Okay, everyone can hear me, I suppose, and you can see my screen.
Yes. Yes.
Thank you. Good morning, good afternoon, and good evening, I think, to everyone, depending on where you are. So we've heard a lot of interesting talks about a new kind of attacks, which adds to the already large list of attacks that exists already. So what I'm going to do is I'm going to try and cover as many different areas as we can, because we have such a diverse audience, I guess, interested in different areas of attacks and defenses, let's say. So who are we? So we are Rambus. We've been in the business for 30 years. In fact, I've been working in security for almost that length of time, not always with Rambus. Rambus acquired division from Inside Secure for the security IP division, and we joined just at the end of last year. So a group of people moved over to work for Rambus, and we continued working in the same areas and some new areas as well. So it's proven to be very interesting, and we have lots of new colleagues and nice shiny buildings, as you can see here as well. So what do Rambus do? So we have security across the entire spectrum of chips, basically. We start off with, of course, cryptography and IPs and engines. We can apply that to different applications. And you can see some of them here already, where we're protecting data when it's stored, maybe just encrypted, or when it's moving around, such as with the internet and IPsec, TLS, these kind of things. But we also want to help set the device up to be secure in the first place, because security and cryptography is not an equal sign between them. There are lots of parameters around about that. Just because you have cryptography does not mean you are secure, as we've been learning this morning. So there's a long list of attacks, and we have some more today, in fact. So the attacks are very varied. We can have logical attacks, where you may be able to do it remotely. It can be protocol-based attacks, all of these kind of things. Then we have the physical and more in-depth and detailed attacks we've heard about today. So I've grouped them into 5 different groups, really. You can subdivide or you can group again, but just for the purposes of this talk, I've added environmental attacks, which is really changing the parameters the device is operating within, such as the voltage or the temperature, maybe providing some glitches in the power supply or the clock. Then, of course, we can have, let's call them semi-invasive attacks, where we want to do side channel or fault injection. Of course, these can be non-invasive as well, depending on how you're injecting your faults or how you're measuring your power analysis or electromagnetic analysis. And then we have fully invasive attacks, which of course are much more expensive. And what I've got here is really the difficulty and the cost and the expertise of the attack tends to increase the further down this list you go. Now, what that also means that we have many countermeasures, and there's actually no one solution to all of these attacks. It has to be combined. Attackers are smart, they keep us on our toes, and a layer of defense is important. We can't just put in one fix and think everything is going to be okay. So let's start with the device lifecycle. So the device lifecycle starts before the device. It starts at the product and architecture definition, not once you've got the product, because it's very hard to paste in security afterwards. You have to think about it from the beginning and think about how we're going to identify that device, what kind of assets are we going to use within that device, and how we're going to get them in there. If I have some debug to do, how do I control that such that engineers can develop their solutions, but not expose weaknesses at the same time? And then importantly, of course, at the end, what am I going to do when the product gets to the end of its life cycle? So moving on to after the product. So then we have the difficulties, and you heard some about this already as well, the manufacturing and test, and the security to make sure that the entire supply chain is robust. We have the software development and debug, as I just talked about there. Once you have some basic information in the device, such as a unique key or identity, you can start using that to control further aspects of the device lifecycle. Of course, the manufacturer of the device is not the only one interested in security, and the customer, the OEM, also wants to add security. In fact, the user may want to add security as well in terms of their own private keys or security or passwords at a very simple level. So we have to be able to support the addition of these different phases of the device lifecycle. As everyone knows, security is not perfect. So once it's in the field and being used, there may be a vulnerability, and we have to have a provisioning process to allow updates to be rolled out over the air or by connection to a computer or whatever methodology it is, but it has to be some way of doing that. And then, of course, at the end, when I sell it or it's broken or end of life, it's out expired, I have to be able to make sure my private information is not available anymore. And this is quite an important one, especially when you think about the larger systems such as cars nowadays, which are really large computing systems nowadays. These contain lots of private information, so when it transfers from one user to the other, we want to be able to remove their assets and things as well. So all of these parts make up the entire product lifecycle. So taking the first area here briefly, so suppliers and manufacturers have got a lot of problems, and we heard in the earlier talks about the possibility of Trojans being inserted in the manufacturing flow. All of these kind of areas are vulnerable, and attackers, as I said, are smart. They're going to pick the low-hanging fruit. They're going to pick the easy targets. So we have to look at the entire security of the device. And because you have keys in the system, it doesn't mean that the key is then put there in a secure manner. So we have to make sure that the chain of certification, or certificate chain, sorry, is robust as well. Going on to device authenticity. So again, we want to make sure the device is what I think it is, and it's not a fake or a counterfeit device. These are very important things as well. So all of these particular areas are in consideration in terms of security. The manufacturing areas themselves have to be secure as well. If you look at some of the highest security products, such as bank cards or passports or medical devices that have security certification, then the security certification, such as common criteria, looks at the entire manufacturing flow as well to make sure that things are transferred securely. The chip is what it is supposed to be. And even during manufacturing, that a bad actor cannot insert himself into that chain and put in malicious data or applications, or even, as we heard, interfere with the process of getting the design to the mask shop and then finally to the fab and to be the final product. But let's assume the device is hacked, okay, and the key is extracted. So it's very important that if every device has got the same key, then the attack is obviously scalable and all devices are broken. And that's obviously not a very good scenario at all. But if every device is uniquely identified and provisioned with its own keys, the attack is limited to that device. And yes, the attacker will gain some benefit, whether it's money or access. But it's not opening up the entire chain of products to being attacked and exploited. And these kind of simple facts means that the attacker is likely to, let's look for something more easy to attack, something I can get a bigger benefit from overall. So again, just looking at the unique identification of devices can be an important deterrent. So how do we uniquely identify devices? So we want to make sure we have a secure chain to do that process as well. And typically during manufacturing, wafer test or even final test, it's possible to put keys or secrets, let's call them, into the devices, and maybe even personalize or customize the operation of that device as well, in terms of features or capabilities. But behind that, we need to have a key management system so that, again, this chain of trust exists, that we are putting in secrets in a robust and traceable manner, so that we can say to our customers or to anyone who's doing this process that this is a reliable, secure process, and here's some evidence you can audit, you can have some security evaluation done in our process and check that things are done well. So as I was saying, the supply chain is very important, and of course the increasing importance comes when you have really sensitive devices going into sensitive applications. It is of course bad enough that your personal device is hacked, but if it goes into a car and the car can be attacked and cause damage to other people or things, then that becomes more serious. And then of course you take it to the next stage where you have military or maybe aerospace level. Again, you can see the increasing importance of being sure of all steps of your manufacturing and personalization processes. And again, the identity is very important as well. We want to make sure we know who is doing what and that they're allowed, authorized, or even authenticated to do that particular activity. And the device ID can be used to authenticate users who have personalized that device with their information as well through the life cycle of the device. The next stage is, we'll just skip through this one quite quickly, but basically what we need to do is be able to ensure that we have the correct firmware or software loaded onto our device. And that way we try to mitigate, again, malicious software being loaded by a bad actor. So here we want to make sure we have a root of trust in your device. That may be an immutable worm or even a sea of gates, perhaps, something that has, is not easily modified. And going back to the initial types of attacks would require great expense to do so. And of course, then once you have the first stage of the bootloader completed, it can pass on to second or third, or how many stages you want to. Each one of these stages can be verified for integrity and authenticity as well. It may be possible that you want to protect your assets even further, such as the program or the software or the firmware you're loading. So maybe you encrypt that as well and add confidentiality to that process. The root of trust, of course, can then maintain the key to unlock that image and allow it to be executed once, of course, it's been validated. A very important part is anti-rollback. We want to make sure that once we have patched, updated, or improved our firmware or software, that we cannot roll back to a previous version where there may indeed be a vulnerability. And we don't want that to happen. So again, anti-rollback is an important feature. And it's critical, in fact, because it's difficult to implement in some cases. You need to have unmodifiable, maybe OTP or something in your device as well. That, again, you have to protect that level of detail such that people cannot modify the OTP. So the implementation of the anti-rollback feature has to be done carefully as well. And finally, of course, we can use device binding to make sure that the software is appropriate for that device as well. Now, moving on to some of the things we saw earlier on. So in side channel attacks, so of course I need to have a diagram to show what side channel attacks are, but basically it's the recovery of signals from the device that can be pieced together to create useful information. Internally, we developed our own solution for doing this because all of the companies I've seen, and everyone has their own homegrown versions typically. There are some commercial tools available, of course, but we had the same idea and we developed our own solutions internally. This is what we use to validate our IPs before we put them to market. This, of course, now customers said to us, well, we want to validate our implementation of your products. Can we do that? So we actually offer this if people are interested to buy it with a set of libraries and tools, of course, to support the analysis. Countermeasures. So we've heard how we can use side channels to extract information. But of course, there are countermeasures we can put in place. Every crypto algorithm is vulnerable, of course, whether it be symmetric or asymmetric crypto. Sorry. We can incorporate power analysis into the IP itself, and these can be done in hardware. Of course, there are software countermeasures as well in symmetric crypto, such as AES or laterally DES, but maybe there's new algorithms coming along. Of course, we have many more linear operations, and these can be easily protected in hardware. But the question you've got to ask is, how much protection do I need? What's the use case for this product? What adversaries or what threat models do I have for this product? And again, what does the attacker gain from this product when they get that? And the reason you've got to ask these questions is that the cost of the product is very important, whether it's the die size or the power consumption. But ultimately, the more security you add in, of course, it will become larger, and therefore more gates are switching. You would expect the power consumption to be higher. So this is very important when you look at different applications, such as battery-based products in the field, such as IoT devices usually are. So these are simple questions to ask before you think about, I just want to have the best of everything. Of course, that's desirable, but what are you trying to protect against? An important question to ask. Now, as we've heard already, machine learning has been around for a long time, and of course, template attacks are a form of machine learning. The training phase, of course, requires you have access for different key values and so on. Masking is effective against such attacks, typically. But more importantly as well, if we can limit the use of keys in the system, that also helps. Limits the training phase. RTL, or the Verilog implementation of crypto IPs, of course, can be strong, offer strong protection. You can also have white box cryptography with protection as well in the software world, of course. With public key cryptography, of course, a regular computation such as a Montgomery ladder is very common to protect against these attacks as well. So template attacks, of course, are very powerful and well known, and has been talked about a couple of times already today. But the traditional techniques, hopefully, are good enough and seem to be strong enough so far to protect against these kind of attacks, even if we can shorten the attack cycle using advanced techniques. So going to typical techniques, of course, for public key cryptography, we have blinding, which is the algebraic methodology of protecting inputs and keys. And for masking on symmetric cryptography is typically done with additive properties. So these typical techniques are still used, are widely used, of course. Constant time operations, very important to prevent timing attacks, of course, in a public key world that is. But a couple of things at the bottom are equally important. These are more simple. Limit the key use. If I need 100,000 traces to perform my attack, then don't allow 100,000 traces per key if you can help it. Or derive keys as you need them and use them. Don't use your stored root key for critical operations. By using derived keys, of course, you'll have the ability to update keys more often, thereby limiting the use as well. I always say to people that a very simple paradigm, if you like, is never store, move, or use keys in plain. You should, because an attacker is not going to maybe attack the cryptographic algorithm, they may attack the movement of the key inside the system from memory into the crypto algorithm, or they may be able to recover keys from external storage areas, but basically never store, move, or use keys in plain. It's a very simple thing to say in one line, but it's a very powerful way of looking at the overall protection methods that you have to put in place for preventing against all kinds of attacks, as we've been talking about. Moving on to slightly more physical attacks again. So I've grouped environmental and fault into the same group here. A couple of reasons. One is some of the countermeasures are pretty similar, and secondly, just to reduce time a little bit because I've got a lot of slides here. Environmental attacks, whether it's changing the voltage or the temperature, are more generally crude than more targeted, precise attacks that we can have with laser fault attacks, for example, that we can talk about in a minute or two. But however, the whole point here is to make the device misbehave and spill some secrets. That's really, or some clues about the secrets. That's what we're trying to achieve here. Clock glitching and power glitching are very strong as well, and of course these can be timed against particular specific operations or areas of operations. However, there's a lot of characterization work required as well to perfect the amplitude, the ramp rate, the position, the duration of the glitch to target exactly what you want to do. What you program, of course, on your tools for injecting glitches is not what actually reaches the gates that you're interested in because of the inherent capacitance and load of the circuit as you try to target the particular operations and areas of the chip. But even then, I can take a step back and say, well, many modern ICs are working at limits defined by dynamic voltage and frequency scaling. So why not attack that? It could be an external power management IC, maybe not being protected as strongly as the actual secure chip I'm interested in. So I'll just play with that as well. Or maybe I want to apply localized heat to be more specific to local areas of the device. So lots of different techniques are available for environmental attacks, but ultimately all of them result in trying to make the device misbehave and spill some secrets or in some way. Typically smart cards and secure ICs have lots of detectors for temperature, for voltage, for clock. These typically require characterization. The objective there is to prevent the device operating when it detects an out of bounds operation condition. Sorry. Of course, that's fine. The difficulty is you sometimes have some false positives, some false negatives as well in there. So you think you've detected something that you haven't, or maybe you want to detect it, but you missed the glitch or whatever it is. So I think sensors are tricky. Most secure products have sensors. They're well tried and tested, but they can be tricky to use and implement. So moving on to more generally fault injection. Fault injection is about control and observability, in my opinion. So what we're trying to do here is control the operation or control the data being worked on, and then of trying to observe what the effect of that change or fault injection was. So we can accurately target specific locations, even bits or flip-flops with laser injection, for example, with electromagnetic injection as well. So we can time the fault, we can do simple power analysis, target particular areas, profile the operations, all of these things that we can narrow down to be very precise. Today, of course, you can have multiple fault injections. Typical lab capabilities today are dual lasers. So doing simple operations like parity may not be sufficient anymore. But of course, if you can inject a fault, you can skip or change the flow of your program or your software. You can skip operations entirely. You can change register bits. These register bits may control security features or responses. You may be able to re-enable the debug mode we talked about earlier that we've disabled for production. Or we can obviously do faulty crypto results to do cryptanalysis later. But all of these types of attack, irrespective of how you're creating the fault, really depend on being able to interpret what the effect is and build on that. A typical fault injection methodology, of course, is to scan the area or maybe the whole chip, but certainly an area of the chip that you're interested in, to look for responses. Of course, that takes many thousands of operations to do the full mapping. And as you can see, a couple of typical responses here. The chip hangs up or the chip resets, depending on what the detection method is doing. The chip may just fall over if there's no security implemented, or the chip intentionally may stop or reset automatically. But the scanning is very important because it does require thousands and thousands of operations typically. We can also talk about differential fault analysis, which again is a style of machine learning where we have to build maybe a dictionary of faults, let's say. These, of course, all lead to the same result of trying to extract keys. So whether we're injecting the fault with whatever methodology, we're still trying to detect that the fault was injected. So that's still needs to be detected basically and dealt with. Take an example of AES. Let the AES do most of the work and attack the last round. Typical type of lab-based or hacker-based attack methodology. So about countering attacks then, so that, as I said, there are many different methods of countering fault and environmental attacks. We can have dedicated sensors, as I mentioned. We can have the CPU operating in a lockstep configuration. What that means is, of course, there are basically two instances of the CPU. Typically, they're operating a couple of cycles out of synchronization so that the single fault single fault injection cannot create the same fault on both CPUs at the same time. We can have parity, we can have logic redundancy or duplication, we can have a CRC of a register, we can have error detecting, error correcting. There are many different methodologies for detecting faults and multiple faults. Of course, with error correcting codes, depending on the cost, you can detect one, detect two, correct one. These are all different options you can have. Another important thing is perhaps the ability to have on-demand integrity testing of the firmware or the software that you're running. Because of course you've checked it when you loaded it in with your secure boot process. But once it's in there, it just statically sits there, let's say. So how do I ensure that it's doing what I think it's doing? On-demand testing is the way to do that, as well as having the protection in the memory of the error correcting or detection or parity you've chosen to put in. You may choose to have so-called canary logic. Canary logic is designed to be the first thing to fall over when, let's say, a voltage glitch or such clock glitching is applied to a circuit. And the idea is this falls over first, raises a flag and says something's gone wrong here, and the system can either abort or decide what to do depending on what checks and balances it has in place. Dedicated IPs, of course, as we talked about, we can have security built into the particular crypto functions, especially that we want to protect. But an important point here is that sometimes giving an error response immediately is not a very good idea in the security world. This is contradictory to the safety world, where in the safety world, of course, in your car, let's say, you want to know immediately something has gone wrong, and in fact, you're measured upon the time to response from detecting to remedying or fixing the problem. In security, we want the attacker not to be given any clues. We want them to continue the operation. We don't want to flag up that they managed to hit something sensitive, let's say, by stopping an operation. So don't always respond immediately. Or if you do continue testing, process garbage data so that the result is confused. In software, of course, there are defensive coding techniques. We can make sure that operations take the correct amount of time, such that the internal state machines or whatever haven't been disturbed, things are operating in the correct order. We want to maybe do repeat or opposite operations, cross-correlate the data. We want to make sure the key and data integrity is checked. Registers can be continuously monitored for faults. And And again, I mentioned about scanning earlier on. So scanning is very important for understanding fault injection responses. Well, let's count the number of errors we get and decide that we're under attack. Because the system normally, if it was random faults from emissions or alpha particles or whatever, then these are rarely going to happen. If you systematically get faults, someone is perhaps tampering with the device and it's time to stop the operation. You may even decide to end of life the device, retire those keys, whatever process you want to follow. But by limiting the number of tests that can be done by an attacker, you can counter their attack. So next is reverse engineering. What we can see here, of course, is that this is a classic machine learning technique where you can reverse engineer by delayering and photographing all of the different layers of your device, piecing the recognized physical structures back together again to create a netlist. Then you can work out what the circuit's actually doing. So there's automated tools for doing this now as well, as you can see referenced there. This can be done in a reasonably short amount of time for a particular cost, of course. So we want to be able to stop reverse engineering attacks. So what we can do here is we can use camouflaged cells such that the automatic pattern recognition software is confused. We have two cells here that look as if they're exactly the same, but indeed the operation is actually different of these cells. The pattern recognition system, when it builds its netlist, it would insert, let's say, an AND or an AND gate or whatever it finds. But in fact, when you simulate or synthesize and try to build that circuit again, the circuit is faulty and won't work correctly because you've built the wrong circuit. So what we want to do here is strategically place camouflage cells into the circuit, and you can use algorithms for working out the best locations to put them, of course. But the reverse engineering tools will fail is the objective in doing this. Another reverse engineering, of course, we talked about storing keys and data inside the device. So extraction of NVM or non-volatile memory data is possible. There are very many techniques. If you're using simple OTP with a fuse, you can basically observe it. But if the more detailed and complex techniques are available as well, like laser voltage probing, you can still extract what would be secret information. So again, I go back to what I was talking about earlier, don't store things in plain text. So random masking techniques can be effective, such that your secrets are stored encrypted or protected in some way, and then the attacker can extract the information, but indeed they've extracted the wrong information. So conclusions, the entire device lifecycle must be designed with security in mind. Uniquely identify your devices is important. Make sure you are running authenticated and verified firmware or software. Make a mechanism available for fixing and patching, because nothing is perfect. There's always going to be something that comes along. Ensure crypto operations are protected, of course, by masking, blinding, or whichever technique you're using for particular operations. It's not always possible to detect an attack that modifies a bit, such as using the sensors, because laser sensors, for example, don't cover the entire chip. They're usually strategically placed throughout the chip. And of course, someone may shoot a laser between them and it doesn't fire, but you should be able to detect the effect of that attack, such as the register you've modified would then flag an error. Manage responses. Always think about the response you have. Again, for reverse engineering, as we just heard, protect against reverse engineering. But again, all of these things are what are built together to make a secure product. No one of these is a panacea. It does not fix everything. So just to finalize, of course, because I work for a commercial organization, I'm obliged to put a slide up with something that we have. So we have solutions that support all of these different techniques that I just talked about there. Finally, thank you. If you want further information, you can contact me directly, or indeed go to rambus.com/security and have a look at what is there. There's lots of information there on different techniques and protections. And at that point, I'd like to invite any questions.
Thank you, Stuart, for a very wide but well-balanced talk. So we do have some questions from the audience. So the first one is that where should be the root key stored?
So the root key would typically be stored in non-volatile memory, OTP. Of course, there are different ways of uniquely identifying a device. You may also have a PUF, a physically unclonable function involved. There's various different techniques, but basically it could be OTP or PUF is the answer to that question.
Thank you. I have actually one question which where you mentioned before during the slides that typically someone would want the best protection possible, like that is a desirable thing, but that is always not possible. So as a product designer, like how would you choose the level of security against cost or different factors?
Mm-hmm. So first of all, you need to understand your threat model. I think that's very important. What am I protecting against? Am I protecting against the casual hacker who wants to break into something just for the fun or to get some information, or am I protecting against the state actor? Am I trying to keep something secure for 3 years or for 30 years? So again, all of these decisions on what is your threat model and what are you trying to protect against, what's the value of what you're protecting, are valid questions to be asking here. And this basically, you have to think about these questions, because there's no point in designing the most secure product in the world that's going to go into an IoT device that will be in the market for 2 years or whatever. So I think, yeah, you have to ask yourself questions about who am I protecting it against, what do they gain if they manage to extract information from this device.
Thank you. There's one more question from the audience. Do you recommend to use glitch detectors?
Glitch detectors, yeah. So glitch detectors again are possible to put in place, of course, and you can tune them for the ramp rate you're trying to detect, positive, negative glitches. Typically, secure ICs of various flavors have glitch detectors in them. However, as I say, they're usually an analog function. Canary logic is some way to try and mitigate these kind of attacks, such as voltage glitches. But of course, the objective of the glitch is to change values internally in the circuit. So a countermeasure, of course, would be to make sure you'll be able to detect unwanted changed values. So I think, again, a combination of things can be effective there.
There is one more question. How would you rate the difficulty of carrying out a power glitch attack, like the clock screw, compared to a side channel attack like a Spectre meltdown?
How would I, sorry, could you say that again? How would I rate?
So how would you rate the difficulty of carrying out a power glitch attack like the clock screw attack versus a side channel attack that is meltdown or Spectre?
So the meltdown or Spectre attacks were really obviously operating in shared space, and that's of course one of the main causes of the problem. So typically a very secure IC would not be sharing memory or cache or anything like that with a general purpose processor. So typically creating a secure enclave or a secure CPU based system would be the way to resist that kind of attack. In terms of glitch attack, then of course access is required. That's one of the important things. Access and the capability to control when and where to eject the glitch, the amplitude, as I mentioned. So again, there's a lot more parameters to play with, I would say, on the physical attack of the glitch. in my view. I think these things tend to be more complex because of the inherent nature of the circuit is different for different products. You have to really characterize each product individually to see what's effective.
You have one more question about trusted execution environments. So the question is that do trusted execution environments, can they be considered as a solution for cloud services? Like, do you see them as a future for security?
Yeah, cloud trusted execution environments, of course, are a valid way of operating in a secure manner. Cloud security, what can I say? I think we have to look at what the capabilities required to be. I think that's the important thing. So again, in trusted execution environments, we are isolating, but it's not completely physically isolated sometimes. So it depends whether you're, again, sharing resources. If you're sharing resources, then of course there's more probability of a vulnerability being identified and exploited. So yeah. It's a difficult one to answer that. I'm sorry, I don't really know a good answer for that. It's a good question.
In fact, like what was common to like a couple of questions about clock skew, spectre, meltdown, and trusted execution environment. Like so, the point is clear. Like the sharing of resources definitely is an optimization, and as we have seen, like any optimization can be a potential security threat given the attacker capabilities. So yeah, they kind of all point into the same direction.
Yeah.
Okay. So with that, I would like to thank Stuart for this very nice talk, and also all the answers and recommendations that he has given after the talk. And with this, I would like to invite Avi to actually share his view about different talks today, and also inform the participants